It's back, so we're gonna get started. So today is my last session with you, and what I would like to do today is to talk about this topic of dynamic pricing, which somehow complements many of the things that we have been learning and discussing in the previous two sections. I mean, it's this important topic for me. I started my career on revenue management, actually trying to figure out how to think about markdown pricing, dynamic pricing. In many ways, everything started for me in this type of research question that we're going to be discussing today. So let me give you a brief outline. So first, I would like to motivate this problem, or this set of problems, trying to give you some sort of a background, so you get a sense of what are we talking about. And then I would like to talk about two papers. One is a classical paper on dynamic pricing with stochastic demand. I put here seasonal product because there's this notion of perishability, or some sort of a short season attached to the kind of products that we're going to be thinking of. And the second is about robust pricing or distribution-free pricing. And so here we're going to be trying to discuss a little bit what happens when you don't necessarily have a good grasp of the demand that you're serving, in some sort of a statistical sense. So what to do when you don't have good forecasts, if you want. And so we're going to talk about that as well. All right. Okay, so just to start, so here's a picture took from some article in the media at some point that kind of shows you what potentially dynamic pricing might mean for some companies. So here we're looking at a microwave. This is the product that we're looking at. And we have three companies. We have Sears, which is kind of out of business. Maybe this chart explains a little bit why. Amazon on red, and Best Buy on green. And as you can see, and we're looking at the price of this product over the course of a day from 12 a.m. to 11 p.m., right? So this is a full day in the life of this product, and we're looking at the pricing. And as you can see, some companies will do what, most of us would think is kind of, the normal way to think about this is that you have a product, it's pretty much a durable product, a commodity in some sense. There's a price for that, and this is $899.99 for Best Buy, and that price stays constant throughout the day, right? But then you have these other companies which actually start looking at the price, and for Best Buy, it's pretty much constant throughout the day. But then here we have some price changes that are happening, right? So in the case of Best Buy, this product had two price changes during this day. And then you have Amazon in red, right? And Amazon is moving all over the place as we look at this pricing. So in this particular day, there was 9 different price changes for Amazon, right? And so the question that we might have is, why this is happening? What is triggering, companies like Amazon here to change the price of this otherwise commodity product, so frequently during the course of just 24 hours, right? And there are many reasons for this, right? There's not just one reason for this. One, standard reason for this is really to try to have some sort of a competitive price with respect to competitors, right? So many companies operating online, which is what we're looking at here, will try to have a price that give them some sort of a position, maybe in search engines, or a position in terms of the price with respect to competitors, right? You want to always be maybe a little bit below your competitors. And so that means that you're constantly tracking prices throughout the web, and not just these three companies, but maybe others, and you're always trying to somehow have a competitive price. And that might trigger, obviously, dynamic pricing as these different companies start kind of competing against each other, right? Now, other things that can influence the pricing here, and that's why I like this chart, because you have, the 24-hour here, is that maybe these companies are realizing that there's different people shopping from these products depending on the time zone where they are. And this might be an attribute or a characteristics of, how much they're willing to pay for a product like this, right? So if you start thinking in those terms, if you start trying to figure out who is shopping for your product at one particular moment in time, and you have some ability to argue that different people have a different willingness to pay for the product, then again you're in a position in which you might be willing to think about changing the price throughout the course of a 24-hour period in order to exploit those different characteristics of the shoppers that you might be facing, right? So so this is what is happening. This is a chart that I took from a paper that focused on Amazon, but kind of give you a sense that this phenomena that we just saw on that oven is not specific to that product. It's something that is happening over and over and over again. So here you have a bunch of companies. In green, you have Amazon, and you see, different categories like electronics and computers in this side, and on the right, you have sports and outdoor goods. So again, these are fairly durable goods for the most part, and yet 15% and more of these items are seeing price change on a daily basis, right? So there is this reality out there. All these companies are selling products that are fairly mature, fairly durable in some sense, and yet we see that prices changing on a daily basis. Now, when you look at the life cycle of a product, and this chart might not necessarily fit every single product that we can think of there, but there's a typical path when we look at the price of a product over time, right? And so there's this introductory price here, which is kind of a low price, and in many cases this has to do with the fact that you're trying to introduce new product in the market, and you're trying to offer some promotions, attract customers, let the natural diffusion process, word of mouth, right, that goes with the introduction of new products to somehow speed up by offering some sort of a low price at the beginning, but then eventually this product will reach a certain level of maturity where you're trying to optimize profits. And so there's kind of this profit optimizing price that you're going to be setting for sometimes. And then we move into this region that might depend on what kind of products you have. Some products might be very good sellers, in which case you can keep a very relatively high price over time, right? Other products might be really poorly selling and might not necessarily be particularly attractive, in which case you need to have much more aggressive markdowns and discounts to make sure that you can sell those units that you have, right? And so there's some sort of a range here of different possible price paths, and this in many ways depends on the type of product and how much the market value those products, right? And so good products can sell at a higher margin, low selling items will need to be sold at a discount, right? And so there's some sort of adjustments that will need to be done as a function of the prices that you have, and other factors, right, like competitive prices that might be in the marketplace. And then finally, you move into some sort of the late stage of the life cycle of a product, in which you need to somehow liquidate that product, move your inventory out of your warehouses, out of your stores, and then move on with new products that you want to bring into the marketplace, right? Now, today we're going to be talking about seasonal products that have relatively short life cycle, and by that I mean maybe a couple of months, and that typically means that you don't see this pattern. You see something that is much more flat, which is essentially you start with the initial markup price, right, and then you try to maximize your profits with the right margin that you're trying to make, but then eventually you start moving into this region where you might need to start doing markdowns, promotions, and start clearing your inventory as you start reaching the end of the season, of the selling season of those products. And so what we're going to try to understand today is how to think about that question, and maybe how to develop the proper mathematical tools that can help us actually come up with an optimal price trajectory for a product. Now, there's many different types of dynamic pricings out there. So, one that I was mentioning when we were discussing the Amazon example with that microwave is this algorithmic pricing, in which essentially you're really trying to code a piece, write a piece of code that will essentially scrap the web and go through the different prices of similar products that you see out there, and you will try to come up with some sort of a business rule that will tell you how you should set your price in response to the prices that you see out there, right? And so this is, algorithmic in the sense that there's some sort of a business rule that's encoded, and then you just let it run. Most of the time has to do with this competitive pricing idea, right? You want to show up as high as possible in, say, Amazon list or in Google list or whatever ranking is being used to to shop for your products, right? And so you try to think about those considerations, and then you try to write your algorithms in a way that it will help you optimize that metric, right? There's other type of dynamic pricing that happen in environments you have imbalance between supply and demand, right? So these are called peak load pricing or congestion pricing, right? So one example could be, the prices that Uber charges, when you want to take a ride, right? So in an effort to increase, the number of drivers driving, during, high peak, we need to increase the price that we charge so we can pay back more to those drivers. So we're trying to adjust the price in such a way that we balance, demand with supply. Electricity, for instance, is priced in the same way, right? So trying to balance demand with supply, right? So that's kind of the underlying principle behind peak load pricing. Then you have this idea of experimental and learning pricing, which is the type of pricing that might happen when you want to learn something about your customers. For instance, their willingness to pay or their, a price sensitivity, elasticities, right? And so what you will do here, you will just change your prices with an effort of maybe doing some sort of an A/B testing so that you can actually come up with data that can help you calibrate better your forecast and learn, what are those preferences and those willingness to pay, right? So that's another reason why you might do dynamic pricing. Then you have pricing that is driven by promotions and marketing campaigns, right? You also want to keep people engaged with your business. You always want them to be paying attention to what you do. And so one way to do these things is by constantly giving them promotion, discounts, coupons, and other type of marketing strategies that can help you, keep their attention. And again, there might be dynamic pricing attached to those things, right? And then we have what I have here in blue, which is really what we like to talk here, which is this kind of analytic pricing or constraint pricing, which is the type of pricing that we have been discussing in this mini course, which is the idea of companies having limited amount of resources and then trying to be smart in the way they sell those resources in the marketplace, right? And the fact that there's a limited amount of them and the fact that they operate in stochastic environments means that you need to be smart in the way you think about this question, right? And so in many ways, what drives this analytic pricing is two things. It's the fact that you have limited resources that you're putting on the marketplace that you're trying to maximize the value, and the fact you operate over short, periods of time with stochastic market conditions. The last that I have here is personalized pricing, which in many ways is just an ability that companies have these days in which they can start narrow the markets that they serve, and they can eventually start charging different prices to different individuals because we have the channels to do that, we have the information to do that, and so we can start tailoring many of these strategies to the individual. And that from the outside, from the market side, might look like dynamic pricing because we see different prices change over time for different people. All right, but again, so there's many different types of dynamic pricing. But in this session today, we're going to focus on this one that I'm highlighting here in blue. Oops, sorry about that. All right, so the canonical example is this notion of markdown management, right? So the idea that companies are trying to, sell products. Many of these products have short life cycles, right? As I said before, a couple of months. And then the question is how you think about a price path so that you can maximize your profitability. And most of the time, this price path is driven by some sort of initial markup price, right? Some people would call this the tag price. It's kind of old terminology when you have physically a tag attached to the product. Those things are not necessarily relevant today when most of the shopping is moving more and more online. And then you have this discounting prices that you see throughout the season as you start selling this. All right. So just to give an example of this, so the idea that we have somehow in mind here is that you pick a particular product, a seasonal product. Again, the season here could be 4 months. And then you start with some initial markup price, you keep that price for some time, and then you might have some promotions. Many of these promotions are really driven by, again, marketing campaigns, not necessarily by revenue management ideas. You need to have Father's Day promotion, you need to have Mother's Day promotion, you have all these holidays, and sometimes you want to also, keep that attention. You have, program promotions throughout the season. And then your price might recover, might stay, but if eventually you're going to move into this kind of portion of the process where you're thinking about doing this markdowns and clearance, right? So this is where you're trying to figure out how to be smart in the way you start discounting the prices of your product so that you can maximize your profitability. And when you start, this is also an important thing, right? So there's research, and we're not going to talk about this today, but there's research that kind of try to think about what's the right time, right, at which you should start doing this promotion in some sense, if you have to design the timing as well. Now, on this graph here, we have some sort of a plot that shows you how, the importance of promotions and markdowns over time in terms of the dollar sale for companies during this period, right? And as you can see, that number has been growing from anywhere between, say, 8% back in the 70s, right? What most of the revenue was made in this portion, right? While today, this number is about 40% or plus, right? So most of the profits and sales are happening during this promotion. So again, many reasons for that. Life cycles are becoming shorter and shorter, so there's more pressure for people to kind of think about the flows of products and how to move them quickly in and out of their systems. There's more competition that obviously put more pressure on your pricing, and there's also some sort of a phenomena of, we have become more and more of a markdown world where people are expecting this discount. People are waiting to see the discount before they start buying. So we have kind of trained our own consumers to expect for this markdown. So there's a lot of different factors that motivate this chart here. All right, so why do we engage in this, right? So of course, why we want to do markdowns and dynamic pricing is because, of course, we're trying to maximize profit, right, of the products that we put in the marketplace, right? So this is really trying to be smart in the way we sell those inventories of products at the right price, right? So that's obviously very important. But another reason why a dynamic pricing tool can be extremely relevant for retailers out there is because they help them manage the flow of products in and out of their system. They help them unclog, their supply chains. If you have a product, you put that product on your stores, it's not selling well, right? That means that that product is taking space of potentially products that can actually sell better that you want to bring into the year. And so how you deal with that problem, well, you can just wait until that inventory gets depleted, but that takes too long. Let's just simply start using our dynamic pricing and markdown tools to just move those merchandises out of the system as quickly as possible. And that keeps some sort of a healthy supply chain moving, right? And this is not necessarily about making money out of that inventory, maximize the profitability. Of course, you want to be smart in the way you do this, but sometimes the main reason for many of this is really to just have that tool in hand that will allow you to say, oh, you know what, let's move this product out. Let's do, some sort of a markdown, aggressive markdown if you want, and get rid of it. The third reason here is because we want to also have a tool that allows us to hedge against many of the possible risks that we face in the marketplace, right? And so the idea here is that, and in this plot that I'm showing you here, is that in principle, in theory, you can think that you have a certain amount of inventory represented by this level here. You have a certain amount of time T that represents the selling season that you have available, and so you would like to see some sort of a trajectory of how your inventory gets depleted, right? And so what happens is that as you go through your process, you start seeing that your realized sales trajectory is deviating for maybe your projected sales trajectory, and there might be many reasons for this, right? There's obviously uncertainty and demand that you're serving, there's volatility, and therefore, it's hard to, follow what you think is the predicted trajectory, but there might be also bad decisions that you have made. For instance, maybe you have too much inventory for this market, or maybe you set the wrong markup price, right? Because again, you don't know exactly how the market will respond, and it's only after a few weeks that you realize, what, that 60% markup that we thought it was a good, it's too high. We need to change that. So we need to react to that. We need to start, cutting that. We need to start doing markdowns so that we can react to that. And so the whole point is that we're trying to use these tools to somehow compensate for that variability and hedge against some of these risks that we face, right? Both from the market and from the own decisions that we make when we decide on inventories and markups. All right. All right, so let me finish this kind of introduction with just an example. So this is a project that I did some years ago with a company called Falabella. It's a very large retailer apparel in Latin America. And so we were kind of working with them because they were exploring more and more these ideas of developing more markdown systems, more dynamic pricing systems. And so we were trying to work with them to see what it takes to do this. And so what I have here, I'm sorry, some of these are in Spanish, but so what I have here is 3 price trajectories, right? And I want to kind of highlight a little bit what happens when you start using these tools and what do you expect to see, right? So this was the trajectory that they had for a product that they put on the market when we were running these pilots. So this red product is some sort of a pan, and it started at some initial markup. So this is not something, these are not dollars, by the way. So it would be a very nice pan if that was the price. So, so this is in Chilean peso. So it was, think of this as maybe $30. And so you start with this price, and then you have some sort of a first promotion, your price drops. And then what happened is after this first promotion, the price kind of stayed, you know, at this level. And then eventually you move into some sort of a markdown phase. And so that this was the path that a typical product was facing back in those days, right? And so what we did was say, okay, let's run some pilots running our systems and see how the price will look, right? So we have different stores, we can run these experiments. So the first one that I'm looking here is the blue one. So the blue one will be, say, let's take whatever inventory you have in the system and let's just price that inventory. And so we will start with a lower markup, right? So here, maybe 20%, 10% less. And the price will stay flat for a few weeks. Again, there's a promotion here. So the system doesn't necessarily have much control on this discount, but then the price goes back, right? And stay again flat at that initial markup. And then eventually you reach a point where you do your liquidation, right? But the important thing is that for the most part, the pricing is much more flat and stable. All right. And then there's a third thing that we did was say, and this is more in terms of whether if we can optimize. So this is a counterfactual really, which is this, if we could set the right inventory for that product, then we will essentially buy less inventory of that product, charge it a little bit higher, but again, the price will be relatively constant over time, and then eventually we're gonna have this liquidation. And so when we look at the values, you know, this is what, you know, we got when you can actually optimize prices for the given inventory that they have, you expect to see your revenues going up by 4.2%. And we estimated that if you were able to control inventory as well, that increase will be on the order of 6.1%. All right. So of course, for them, this is huge, right? So this increase in revenues of 4% has a huge, huge impact on the bottom line, right? And so they were obviously very excited about this. The other thing that makes a lot of sense to them, and it was as valuable, was the fact that these pricing tools are much more stable, right? And so this again has to do with the fact that when you have a price trajectory like this red one, and you have consistently this price trajectory, consumers get used to this, all right? And so many people that potentially could have bought this product at the beginning of the selling season at this initial markup might just simply decide, you know what, why don't we wait? I know in a few weeks, this is going to be discounted 20%, right? So again, these red curves train your consumers to wait, right? While this blue or green curve that I'm showing you here have less price volatility and will essentially lead to less, gaming or less strategic behavior from the part of the customers. There's no point to wait, right? You only wait until the very end, but if you're trying to buy some sort of a seasonal product, you want to use it this season, so you don't necessarily want to wait until the very end. And again, when you wait till the very end, you take the risk that, the size that you're looking for, right? Maybe the color that you're looking for is not available at that point. So there's some sort of a scarcity risk that consumers will take, right? So being able to have this more stable pricing was also a very important part of this pilot that we were running. All right. Anyway, so with that, let me move into a little bit more of the theory, right? So let's talk about the theory of this dynamic pricing. So there's this very famous paper that Guillermo Gallego and Ryzin wrote in the 1994, and it's a paper that has thousands of citations, has become one of the most visible papers in this area. All right, and it's it's for many good reasons, right? So let me try to explain this paper and how it works and how this essentially gives us some sort of a framework that we can use to start thinking about some of these questions that I was mentioning before. Right? So let's on the seller side, all right, on the company side, we have some inventory of some seasonal product, could be perishable product. Right? And so there's two characteristics. So this is some sort of commodity in many ways. There's a certain initial inventory, let's call that C units of inventory, and you have a certain amount of time, T, to sell this inventory, right? And the way I would like you to think about this is that these are two dimensions, right, of your product, right? So there's an inventory, so there's a quantity, so this is one resource that you're managing, which is how many units you have. But there's another resource that you don't control, but it's also somehow a resource attached to this problems is the amount of time that you have available to sell it. All right. And so that's as you will see in a minute, these two quantities will define the state space of the corresponding problem that we're going to be solving, right? So inventory available and amount of time that you have. Now, on the flip side of this market, you have your consumers, your potential consumers, right? And so there are many of them. And there's two things that characterize this market. One is some sort of the arrival process. So how these people eventually come to your system to buy, right? So there's eventually people will come and shop at your store, at your website. So there's a certain arrival process that we need to characterize to describe that. So that's kind of part of your demand forecast. And the second characteristic of this individual is they have a willingness to pay, right? So this is some sort of a way to conceptualize the demand process. And the way we're going to do it is by thinking that each individual has a number in their head that I'm going to call W that represents, how much they're willing to pay for this product that you're selling. All right. And so some customer comes. So let's call this customer customer T, because that customer is showing up at time T. So this customer at time T shows up with a willingness to pay WT, and then goes through this mental process, right? See your price, PT, and ask the question, is my willingness to pay greater than this price? And if the answer is yes, then that customer will buy because he's willing to pay more than what you're charging for the product. In that case, the seller collects that price, of course, but has to give up 1 unit, right? So the inventory gets depleted by 1 unit. On the flip side, if the answer to this question is no, then that customer doesn't like your price and simply leaves the market and doesn't come back, right? So again, so this is kind of the basic framework. You can imagine people that maybe go back and come later, maybe waiting for the discount price, or maybe more strategic behavior, right? So you can start, changing some of these features, but this is the basic model that we're going to be discussing, right? And so one thing that I want to mention again is this notion of the willingness to pay, because I know Omar is going to be talking about this, I believe on Friday when he talked about his paper. And one thing that is central to his research in this paper is really what we know about this, how much do we need to know about this, right? So a lot of questions about this quantity that today we're just going to simply assume that is a random variable for which we know the distribution, right? So we're going to assume that different individuals, of course, have different valuation, but there's some sort of a distribution of willingness to pay in the market, and that distribution is something that we're gonna assume we know. All right. All right. So let's formalize that model. Right. So the model that we are looking at is one in which we're trying to think about how to optimize that price trajectory, those PTs that I was showing you before, in order to maximize your profitability. And so what's your revenue is, again, the integral from 0 to T of the price that you charge, right, times the demand. So think of it, AT here as your arrival process. So every time that the arrival process jump by 1, that means that the customer is arriving to the market. But again, that customer will only buy if the willingness to pay of that customer arriving at time T is greater than the price that you're setting at that time. So this indicator function is really taking care of that decision that the customer needs to make, whether yes or no, based on you buy or you don't buy, right? So this is how you accumulate revenues over time. But of course, we have this limited amount of resources. We have C units, and therefore this integral here, this stochastic integral, represent your sales process, has to be always below C, right? Almost surely, right? Because eventually you cannot sell more than what you have. Now, the second constraint here is an abstract constraint, which says that the price process that you're going to be looking at has to be, has to satisfy some additional constraints. And I'm going to, in the next slide, I'm going to talk about what these other constraints could be, right? But again, the notation, again, T is the selling horizon, C is your inventory, P is your price trajectory, WT is your willingness to pay, the willingness to pay of the customer arriving at time T. We're going to assume that there is a distribution F, right? Probability distribution F for the willingness to pay of those population that is known to the consumers. A of t is this arrival process that we're assuming here is independent of the price process. So in some sense, in this model, we are decoupling. So there's a process that describes how people get interest in your products, go to your store, go to your website, and then there's a second stage in which they buy or not buy based on this willingness to pay, right? So that's why this arrival process here is not a function of the price, the willingness to pay, and that decisions will take care of that. And finally, we have this set of admissible, pricing policy. Of course, adapted is the most basic condition. You cannot see the future, right? You don't know how many customers will come in the future. So your pricing need to be adapted to the history of this process. All right. Let me see if there's any question about this, the mathematical formulation here. All right, very good. What are some of those real constraints that potentially can characterize that set P that I was describing before? So some constraints could be only markdown. So your price can only go down over time. It cannot go up or down. It's only markdown. We're not going to look at that in this discussion today. That paper that we're going to discuss doesn't take care of that. But in some applications, you can imagine that you need to impose that constraint. The price can only go down. You cannot increase the price. Another constraint that you might have is that you cannot change the price any minute or any second. You need to only change maybe the price 3 or 4 times in the season, right? You need to announce this price. You want to create too much volatility. Many reasons why you might want to restrict the number of price changes. So that might be another thing. Maybe you have different selling channels. You sell on your stores, you sell on the web. Maybe you sell through companies, through sellers that take care of that specific channel. Maybe you need to have consistency across the prices that you set on these different channels. That would be another constraint that you need to take care of. Another constraint, which might be very practically driven, is the idea of cost-based pricing, which is that sometimes for people it's hard to set or charge prices that are below their costs, right? For them it's some sort of taboo. This is something that we don't do, even though this might be the best thing to do, right? And so sometimes you have some business constraints like cost-based pricing that also limit the type of prices that you can set. All right. So these are constraints that you might have on that model on the price side. Now, other constraints about the model more generally is that, again, demand forecast challenges. Maybe the demand is not stationary, right? So there might be something. Again, you can take care of that. But maybe the market might be driven by, maybe some sort of a Markov chain modulated by, right? Like shocks in the market, right? Might potentially drive factors of your demand. So how sophisticated is your demand forecast, right? So for the moment, we're going to take a very simple version of that. It's going to be a stationary Poisson process, right? But this will be a question. The other one is how much you know that demand, right? And again, there's going to be one module in this course that you're taking that's going to spend a lot of time talking about demand learning, right? About the idea that I don't know my demand, but I can learn that demand, right? So how my prices can help me to do that, right? So that's another thing. Competitors' actions, right? So what happens if you have to react to competition in the marketplace, right? There's some research that it has been done in this area. I would still argue that there's a lot of opportunities to do better, not better, but more research, I should say. There's good research out there, but more research on this particular issue, right? The competition. Strategic consumer behavior, right? So here we're going to assume that these people come through this mechanistic arrival process, this Poisson process, but there's no strategic behavior on their part. They come, they see a price, if they like it, they buy it, otherwise they go, right? So very mechanical buyers, but in practice, you might expect people are much more strategic. So how to handle this? And finally, how it happens when you have multiple products, which might be substitutes, right? And again, you're going to be having, I believe the next module, I don't know, is on assortment planning. And I bet Hussein is going to be talking a bit about the interaction between assortment planning and pricing, meaning how should you price menus of products, right? So you don't just have one type of inventory, but you have 4 or 5 different types, which might be substitute, and a customer might buy inventory 1 or inventory 2 or inventory 3, and that decision might be affected by the price that you set for each one of them, right? So there's a lot of setting and practical considerations that we're not going to be capturing today, but hopefully as you continue attending this program, you're going to see many of these issues coming back, and this is going to give you the proper tool to start dealing with many of these. All right, so how we formulate this problem, right? So let's start with it's a continuous time version, but let me start with a discrete, which I think is easy to think in those terms. So take your selling horizon, And let's just divide them into some sort of small time intervals of length dt here. All right, so I'm going to have capital N of them. All right, now within each of these intervals, we're going to ask the question, well, what's the likelihood that a customer will show up, right? And so we're going to call that, say, Qn. So Qn is the probability that the buyer arrives, right, to the system. And so, for instance, if the underlying the arrival process that we are going to be using, which is what we're going to be using really, is a Poisson process with rate lambda, right? So the likelihood that we have an arrival epoch is proportional to the length, lambda times dt, right? Plus a bunch of terms that are order delta t squared, right? So essentially, if delta t is relatively small, right, these terms here will be somehow negligible. So you can think that the probability of a customer arriving at time, at this interval, I should say, n, is lambda delta t. All right, so that's one piece. The second piece is that in that interim interval, we have a price, right? So we have, this is our price trajectory, which is discretized in this case, right? And so given that price that we're setting, one minus, remember, f of p is the cumulative distribution function of the willingness to pay. So 1 minus fp, which we're going to call f bar of pn, is really the probability that a customer will buy, right? Meaning the probability that the willingness to pay of that customer arriving in this period n is greater than the price pn, right? So this is kind of the right tail of the distribution of willingness to pay, right? So because the willingness to pay has to be greater than the price for people to buy, all right? So this is the probability. And then we're going to multiply this probability of purchase in this probability of arrival to define this quantity lambda n of p, which is essentially the selling rate of the demand rate that you face during period t, right? So a customer, you're going to have a transaction if two things happen: a customer arrives and the customer buys, right? So the product of these two things is really the probability at which you're going to be selling, right, during that period. And that because we're looking at these periods through the optic of this delta t, we can think of this as selling rates during that particular period. All right. Okay, so that's how we discretize. And so with that discretization, we can kind of go back to some of the things that we did, last week and kind of write our dynamic programming equation. So Vn of Cn is the optimal revenue to go if you start in period n and you go forward, if you have n periods left, right? So I'm going to highlight this because this is a little trick that people use. It's a convention really more than a trick. And so instead of counting time forward, which is kind of done, we're going to count time backwards. And this is useful because remember that I said that you want to think about, you have two resources that you manage, the actual inventory and time. So with this characterization, you can think of n as a resource. How many units of resource you have? You have n units of time and you have Cn inventory, right? So these are the two resources that you have at this particular moment in time, right? So that's why n here represents how many periods you have, right, to manage, right? All right, so what is this revenue to go? Well, you're gonna have set the price on this period n. Now this, remember, is the probability that you sell a unit, is the composition of a customer arriving and buying, right? And so if you have a transaction, then you collect the price, but then your inventory get depleted by 1 unit and you move to the next period, and that's why your number of periods left also get depleted by 1, right? So you deplete both time and inventory in this case. Now in this, but then there's a chance that nobody buys, either no one shows up, or if someone show up doesn't like your product. Anyway, 1 minus lambda pn is the probability that you don't sell a unit. And if you don't sell a unit, you have the same amount of inventory left, but again, you have 1 period left, right? So your inventory stay the same, your inventory remaining gets depleted by 1, all right? So that's your dynamic recursion, right, for this problem. And the boundary conditions, of course, is that you don't have any inventory left, there's nothing for you to sell, so your value will be 0. And if you have no time left, right, again, your inventory is worthless, and so you make nothing, right? Again, you could change this and maybe say that there's some salvage value here, right? That's possible, but again, this setting the basic assume no salvage value. All right, so that's your Bellman equation in discrete time. And then what we're gonna do, we're gonna essentially take a limit as the interval in between periods goes to 0. And we are going to derive this Bellman equation, this AGB equation, the continuous time, right? So the partial derivative of your value function with respect to time is equal to the max over P of this expression that I have here, all right? Now, maybe you have seen this before, maybe you haven't. You can start, if you want to review this later, you can start playing with this discrete equation. This one times this function, you can pass that to the other side. You can divide, remember all this lambda t's have a delta t embedded. You can divide by delta t, and then you can start kind of convincing yourself that this is indeed the continuous time version of this equation star that I have here, right? Now, again, just to reiterate something that we learned last week, when you look at the optimality condition here, you would obviously set a price that is greater than the difference of this, right? So you want at least this, you don't want to set a price that gives you negative revenue, right? So this is some sort of a notion of incremental or displacement cost that you want to calculate, right? And shows up again here. The other thing that I want to say in this slide is that there's a certain curse of dimensionality with dynamic programming, right? So if you have, say, in this example I give you here, say 1 product and 200 units and say 100 sub-intervals, you will need to be solving 20,000 optimization problems like this in order to solve the discrete version of this, right? And that's not too bad. But what happened if instead of being thinking about optimizing the price of 1 product, 1 resource, you have 3 resources? Again, we're not going to do this here, but it's not an unrealistic situation. 3 products that might be substitute. Well, in that case, with 3 products, you will have to solve more than 800 million, right, optimization problems. So it grows very fast, right, with the dimension of the number of products that you are selling, right? So there's this curse of dimensionality that attaches to this dynamic programming. And so this is just a warning. We're not going to have to deal with this in this discussion I'm giving you here, but it's a warning that you always need to look at this dynamic programming in these environments and keep in mind that as the dimensionality of your inventory here start to grow, the complexity of this dynamic programming in terms of explicit solutions grow exponentially fast, right? And so sometimes either it's impractical to try to think about solving a problem using dynamic programming this way. Okay. All right. So what can we say about that dynamic programming solution, right? So people make this assumption. Again, it's a very common assumption. It's regular. It's not particularly restricted, I would say. So the first one that we're going to make is that this demand process is stationary. So that's the first thing. Both the arrival process and the willingness to pay of the population are stationary, so they don't depend on time. Second, we assume there's a price sufficiently large, they call it P infinity, that this arrival rate is actually equal to 0 if the price is very large, and the revenue per rate that you make is also 0, right? So again, this is very realistic. If you charge a very, very high price, nobody is going to buy this product. And so this is not a particular restrictive. The second is that lambda P admit an inverse, right? And again, this is just, it's also intuitive. If we think about this as some sort of demand function, this demand function is, decreasing in the price. So if it's continuously decreasing, we're going to be able to define some sort of an inverse for that. And the last thing is that this revenue function, so if you multiply lambda times P of lambda, the inverse, so this is some sort of a revenue function as a function of lambda, is a continuous function, it's bounded and it's concave, right? And in particular, there's an argmax, which is the value that maximizes this instantaneous reward function. Now, the first proposition is very trivial. I mean, you need to prove this thing. So, everything here, everything here is modulo, you need to prove it. But the intuition, at least for this, is very, very simple. Let me just kind of show you, let me open a page here, show you exactly what I want to say here. So this says that if the function, the demand rate is regular, then the optimal selling rate, right, that you would like to set is always bounded about by lambda star, right, by this argmax here, for every inventory and every time that you have left. And the picture I think that you want to somehow look at is just a picture that looks like this. This is your R of lambda, so revenue rate as a function of lambda. And so here you have your lambda star, right? And so what happened here is that what this proposition is saying is that you always going to be looking at this portion. This is where your optimal strategy is in terms of selling rate. You're never going to be looking at values of lambda greater than that. And the reason for that is very simple, because if you pick, say, I don't want to do that. If you think that this lambda hat here is an optimal selling rate at some point in the selling process, I will come to you and argue, no, look, there's this other rate here, let me call it lambda bar, which essentially gives you the same selling rate, right? So they give you, you're going to be generating the same revenue per unit time if you set lambda bar, right? But this one consumes less resources because you're selling at a lower selling rate, right? So you're actually more efficient in the way you generate that revenue because you allocate less resources. And obviously, having more resources is good. So that lambda bar dominates that lambda hat, right? And that's why you're always going to look at optimizing in this region that I'm pointing you here in red. Okay. I don't know if there's any question with this logic at this point. All right, so that's one kind of statement. The other statement that you can do, and I'm not going to go here. It would take too much time to really prove something like this, but it's essentially that this value function that we have for the problem, which again, T is how much time you have left, C is how many units you have left, satisfy all this monotonicity properties. So it's strictly increasing in the argument. So again, if you have more time, you're going to make more revenues. If you have more inventory, you're going to make more revenues. That it's also strictly it's, I should say, extremely concave, sorry, in both C and so there's these utilities of the marginal revenues of more inventory and more time, it decreases, right? So there's some sort of diseconomies of scales on those two, which makes also sense. And then this function lambda star that I was showing you before, which is the optimal rate at which you're going to be selling your products, satisfy also these monotonicity properties. Okay, so a lot of the papers, if you start looking at the literature especially back in those days, about in this area, you will see that many of those papers will have statements like this. They will formulate some sort of a dynamic program that try to characterize the value function, and they will go and try to understand what are some of these properties about this value function in terms of the value, the marginal value of more resources, more time, and also about your optimal pricing strategy or selling rates here. Okay. So this is how a solution will look. So this will be the path, right? So here you have your selling process. So this is your inventory, nothing is happening, and eventually you have a sale, right? And so as you can see, while your inventory is flat, you're not selling, your price is going down. So in other words, as you have less time, that puts more pressure into start marking down your price goes down, but eventually you have a sales, and as your sale goes down, you have less inventory, so your price goes up. And then again, there's no sales, your price goes down, and you're gonna have a sale, your price goes up. So you can see that the path of your price is responding to your level of inventory. And during those periods of time where you're not selling, your inventory remains constant, your price is going down, and every time that you have a sale, your price goes up, right? So that's kind of what is happening. As you can see, this is theoretically sound, but for practical purposes, it might not be very realistic. And that's why adding some additional constraints like, oh, you cannot change the price more than say 4 or 5 times would somehow prevent this kind of very erratic price path that is coming out of this particular model, right? All right, now what else can we say about this? So that paper is very influential because it proposes a model like the one that I just showed you that captures some of the essence of the problems that we have at hand, but also develops some asymptotic analysis that have influenced a number of people in the way they think about solving this. And so we discussed this last week, and I'm going to kind of reiterate this one more time. So one type of asymptotic analysis that we can do is based on this certainty equivalent or fluid version of the problem, right? So this is the same optimization problem that I was discussing before, but now we're going to remove all the uncertainty, and we're going to assume that people are coming as a fluid. Instead of a discrete Poisson process, think about people coming as a fluid, and the revenue that you generate is the same R of lambda that we have here over time, but there's no expectation here. And then instead of having a stochastic integral that describe how inventory get depleted, we're going to have this fluid version that describe how inventory get depleted, where the rate at which we're depleting the inventory is precisely lambda s, right? And so here, as you can see, I'm not formulating the problem, this fluid version, in terms of prices. I'm formulating this problem in terms of intensities. But remember, there was a one-to-one correspondence between the price and the demand intensity. So this is one of the assumptions of a regular demand function. And so the deterministic solution essentially does this, basically solve this problem, right? Now, the first thing to notice is that this is a relatively trivial problem to solve, right? So again, let me try to convince you. So we're trying to solve this problem. We're trying to maximize the integral from 0 to t of r lambda s ds, subject to the integral from 0 to t of lambda s ds, says less or equal to c. All right, so that's kind of the problem, and we're maximizing over lambda. So remember, lambda star is the arg max of r of lambda, right? And so if you could set this lambda star at all time, that would be the best that you could do, right? If you can maximize, the argument of the integral, that obviously will maximize your cumulative payoff, right? And so the question is, well, can I implement that policy? So if the integral from 0 to t of lambda star ds is less than or equal to c, then that will be feasible. If you have enough inventory so that you can set lambda star at all time, then that's the best thing to do. And so this is equivalent to saying that lambda star t is less than c. So in this case, right, if this is true, right, the optimal strategy is to just set lambda s, and we go star for to be just this lambda star. Okay? But on the flip side, if you don't have enough inventory, if the integral from 0 to t of lambda star ds is greater than c, then you cannot implement that policy. But that's when you go back to my little plot that I showed you before, right? This is lambda star, this is r of lambda. So if you cannot implement this, you're going to implement a lambda, which is again smaller, but so that but it's as large as possible. So essentially, you're going to solve for a lambda. Let me call it. Can't remember if they use annotation. Let me put bar, such that the integral from 0 to t of this lambda ds is equal to c. So essentially, you want lambda bar times t to be equal to c. So lambda star s in this case will be essentially equal to your capacity divided by t, right? So this is the optimal policy, right? And so that's basically what you want to do in this very simple problem. So your optimal solution is to pick the minimum of those two things, right? So your optimal solution, you combine these two, so optimal strategy to pick a lambda s, which is the minimum between lambda star and c over t, right? So that is very, very simple, and in many ways follows from the concavity, if you want, of your revenue rate. Okay, any questions? All right. All right, so that's precisely what we have, and then you can compute the corresponding revenue attached to that policy, which is once you plug that solution, you can compute this, what I'm going to call VD, D for deterministic. All right. All right, so this is just a benchmark, right? So this is something that you can use because it's somehow easy to solve and kind of take the spirit of what we were discussing last week, which is trying to remove the uncertainty and look at the fluid version. Now, the first results that Garrett and Guillermo proved in that paper was that this deterministic solution that I just showed you is an upper bound for the optimal solution, right? And we kind of discussed this last week again. So this is some sort of a reiteration of a result that we learned last week, which is that these fluid solutions typically give you upper bounds on the value of your dynamic programming. All right, so that's good. Now, the second thing that they show is that if you take that policy that I was showing you, right? So again, if you take this policy, right, that uses this minimum, and you implement that policy will generate a value, which is just, you know, the value of that policy, and that value of that policy satisfied this ratio here, which is the ratio of that policy to the optimal one is bounded by 1 minus this ratio. And why this is important? Because obviously this is always less than 1, right? Because the optimal policy V star always generate, you know, higher profits than your fixed policy, which is just a 1 policy, but it's bounded below by this quantity. And why this is useful is because this gives you a sense that if this, you know, minimum here is large, then this fixed price policy is actually asymptotically optimal, because, you know, it will be right. And so again, when this minimum here can be large, when both X is large and lambda star T is large. And so this kind of give you again a sense of those regimes that we were discussing last week, if you remember, where we were saying that if your inventory grows large, but your demand, the mean demand grows large, then, you know, you expect that these fluid policies will do well. Well, this is precisely a way to see that in this particular proposition here, right? So if X goes large and lambda goes large, if they both grow large, and remember lambda star T is there some sort of a minimum, an average sales rate at the value of lambda star, right? So that's what they prove. And then in a paper that I wrote after with Gabriel Bitran, where we're kind of analyzing some of these policies, we kind of saw that, you know, there's some alternative way to think about this asymptotics in terms of the coefficient of variation of the demand at a particular price, right? And so what we saw is that one can reinterpret some of this and also extend it into non-Poisson discrete models in which you can have that indeed the ratio of the value under a deterministic policy divided by the optimal is bounded below by 1 minus the coefficient of variation of the demand over 2 at a particular price, right? And so in the case of a Poisson, that coefficient of variation takes this particular form here, right? But in reality, what you're looking at, or you can say that these deterministic policies are kind of optimal when you have this kind of intuitive statement that if there's little variability per unit of demand, right? So coefficient of variation, remember, is the ratio of the variance divided by the mean. So in this context, saying when the volatility of your demand with respect to the mean demand is low, you expect deterministic prices to actually perform well, okay? All right, so I was planning to go through the proof of this with you. But, you know, all right, let me just give you some sort of a sketch, right? Because I want to move to the second part where we talk about the other paper, but let me just give you some sort of a quick sketch of how the proof of that inequality works. So, all right, so basically what we want to show is the following. We have this VFP, which is the value function under the fixed policy for a given, say, time t. I'm going to use X for how much inventory you have left. And again, because of the definition, this policy is just the integral from 0 to t of R of lambda. I'm going to call it D, which is the intensity under that deterministic policy, D tau, subject to, and then we don't need to worry about the constraint because this policy is obviously admissible. And then we of course know that this is less than V star because V star is the optimal, all right? So now how we can think about this. So this is really the expected value of the price under this deterministic policy times the minimum between the sales that you're going to have under this deterministic policy and, right, and X. So because you fix the price, you can see how many customers will want to buy. That's essentially S of T, and X is how much inventory. So the minimum is how much you actually going to sell times the price, which is this fixed price, and that gives you a revenue. All right. And then you do this little trick where you rewrite this minimum as STD minus STD minus X positive part, right? So remember, if S is greater than X, this is the difference, but if S is greater than X, so this is negative, the positive part will make this equal to 0, right? So that's precisely what that positive part means. And then from here, you can use a lemma that Guillermo proved in a previous paper that says that for any random variable S with expected value with mean, let's call it mu, and variance sigma square. So you give me a random variable, then the expected value of S minus X plus, so the expected value of that positive part is bounded above by sigma square plus X minus mu square minus X minus mu divided by 2. So this is some sort of a Chebyshev type of inequality, right? So you essentially are trying to bound the expected value as some sort of a functional in terms of the first 2 moments of that random variable, right? So, and so that's basically what you can use here. You can say, okay, VFP is equal to the expected value of PD times SDT minus, and then you can replace that. So it's going to be greater or equal. So I'm going to use an equality, sorry, here, because we're going to replace this expectation of this term with this upper bound. And so we're going to get this lower bound. And so it would be the square root of sigma square of that S. I'm going to put it here, minus X minus mu S, which is the sales process, square minus X minus mu S divided by 2. And then, and this is where I'm going to stop. Basically, I'm going to give you, I'm going to kind of leave it here. So I think you can complete the following step, because you have then 2 cases. Remember that the deterministic policy has 2 cases. If you have a lot of inventory, then you can set lambda star. But if you don't have enough inventory, you need to put that constraint price, right? So in case number 1, which if lambda star T is greater than X, so you don't have enough inventory, then what's going to happen here is that the sales process, so your mu S is going to be equal to X, and your sigma square S is also going to be equal to X, right? The sales process is going to be limited by your inventory. And in case number 2, your this is when lambda star T is less than X, so you don't have enough inventory. So in this case, your your sales process, the mean of mu S is going to be just lambda star S, and the variance is going to be, the variance of a Poisson is equal to the mean, so it's also lambda star S. Okay? So you have these 2 cases, and then essentially you're going to plug those 2 cases in this inequality, and you're going to manipulate them, and that's going to give you precisely what you want. All right. So let me just leave it at that, because the rest is really algebra. I think what is insightful in some sense about this proof is, well, first realizing that you can write the profits using this expression here, and second, this little lemma that is actually quite useful, not just for this, but for other type of application where you have these positive parts that bounds, you know, the expected value of this positive part in terms of the first 2 moments. All right. All right, good. So let me just with that move a little bit into the rest of this discussion that I want to have to do with you, which is that what happens when you have robust pricing. But just to give you a sense of how this, you know, literature has grown and what are the variations that some people have considered over time. So people took this paper and start kind of working on it and expanding them. And so you have papers that have looked at what happened when you have monotonistic prices, monotonistic price path, right? So price that can only be markdowns. And, this is the paper that I kind of get me started doing this when we were looking at those type of issues. Then there's people have looked at what happened. You have limited number of price changes, maybe 1 or 2 only. And so here you have some references. If you're curious about that, that will tell you how to think about adapting this methodology to that case. Then you have people that thought about what happened if you have unknown demand rates, right? And so with Victor, we were looking at that at some time ago, and there's other people, Omar including, that's going to be talking on Friday, that have been look at that question, right? And then you have people have said, what happened? You have strategic customers, right? People that are a bit more smart and they can anticipate, the fact that you're going to cut the price. And so there's research that has been done, like this is one of the first paper by Aviv Pascal, but Garrett also has a paper with a student, former student, that we're looking at this. So these are just a few references, but there's hundreds of different papers that have been extending this framework. All right. So hopefully this will give you a little bit of a feeling for what that framework is, what is the kind of approach, and also what are the extensions. But let me spend the last 20 minutes talking about some sort of a related question, but somehow in trying to questioning some of the assumptions that we made in the previous approach, right? And so this is based on a paper that I wrote with a former student, Ying and Ilan Lobel, and it's trying to ask a question about what happens if you don't know much about the demand, right? So just to motivate this, some kind of numbers. So there's a McKinsey study that kind of look at this question of how many products companies are bringing to the market, and there's a lot of them. How many of them are failing? A lot of them, right? So this is the business. Companies are really trying to come up with new ideas, trying to be competitive. New products are being brought to the marketplace, and not all of them just succeed. Only very few, if you can say, actually succeed. And part of the reason is that companies are not necessarily very clear about how to price this, right? Many other reasons, of course, but pricing is one of them. You bring a new product, right? And then you don't know exactly how much customers are willing to pay for that product, and then you start coming up with the wrong markups, and then that's triggered part of the problems that drive these products to fail, right? All right. Now the other thing that I want to highlight and which is important in the way we're going to think about this problem is that people are strategic. People are not passive agents that don't necessarily pay attention to what's happening in the marketplace, and they are better equipped these days because with e-commerce and web aggregators, they can actually, social media, they can communicate opportunities in price. They can kind of understand better how companies are pricing their products, and therefore react to that information in a way that potentially is gives an opportunity to maybe buy when prices are low, right? And part of this is, as I mentioned before, is self-inflicted. This is again similar to that chart I showed before. How much of the stores' dollar values are actually done on periods of markdowns, right? So this number is going up, and so people are used to markdowns, right? So we have these two, and kind of to reiterate that, take this example that I borrowed from a paper by Hendel and Nevo. So this is the price of a 2-bottle Coke over 50 weeks, over a year. And so look at how this price is looking at, right? So if you are a strategic consumer, right, and this is a product that you can store at home, it seems pretty obvious that if you know that it's the price path, why to buy a product when it's high, when you wait maybe a week and you can buy the same product at a discount, right? So this is a classical example of a product that companies are offering through this kind of zigzagging price strategies, full price discount, full price discount, and then anyone going to that retail store on a regular basis will be able to learn this and start acting and reacting to these price changes, right? So we cannot simply pretend that consumers are just this mechanistic, individual, just show up, see a price and buy. You expect people to be paying attention to these opportunities, right? So what we ask ourselves in this research was, well, essentially, how can we think about price paths when there is incomplete demand information? So we don't know really, how much people are willing to pay for this product. This might be new products, right? But also people are strategic and they can potentially anticipate the fact that we're not going to be discounting, right, the price over time, and therefore they might be willing to wait for that. Okay, so in order to do this, we need to somehow have the right framework. So what's the proper way to think about, answering this question, right? So I need some notation, at least I need some framework, not really the notation, it's more about the framework that I need to build here with you. So take essentially an optimization problem. This is what we're trying to do. We're trying to optimize prices. So typically we have some sort of a objective function, I call it payoff here. And that objective depends on the action that I'm going to be taking. Those are my prices, but also depends on the uncertainty, and this might be customer arrivals, willingness to pay, and so forth, right? So what we just did in the previous paper was to use this expected value maximization approach, which was to say, all right, I'm going to assume that I know how this uncertainty behaves, and that is some probability distribution Q, right? That belongs to a set of possible probability distributions. Then I'm going to compute the expected value of my payoffs. And then I'm going to ask myself the question, what's the action that maximizes the expected value of my payoffs? All right. Okay. So this is the standard way that we do, optimization, stochastic optimization, right? But it relies on this, right? And so this is precisely what we're questioning here. We know the distribution, right? Sometimes we don't know. So there's an alternative approach, which is this max-min, which is to say, well, maybe we don't know the actual probability distribution, but we know a set of probability distribution where this probability distribution belongs to. So people will call this an uncertainty set. Okay, so if I am giving myself that leeway, which is I think I know it's the uncertainty set, maybe I can think about this kind of worst case optimization, which is I pick an action, and then quote unquote nature picks a probability distribution from that set, and then we compute this expected value. And so what I want to do is I want to pick an action that maximizes the expected value, but nature will pick a probability distribution that wants to minimize that expected value. So I'm competing against nature. And so this is some sort of a worst case type of analysis, because I'm assuming that nature is antagonistic and is always looking for ways to hurt me by picking a distribution of valuations of consumers that can hurt me. Now, this is possible when people have looked at this. Now, one notation here is this delta means that now you can potentially randomize your actions. It's no longer obvious that you want to have deterministic actions. You might want to have stochastic action in this context. Now, this can be very conservative. That's a problem with this criteria, right? So if your uncertainty set is relatively loose, you can end up with situations where nature always picks a distribution where the valuation of customers says always 0. And if customers have always 0 valuation, there's nothing for you to do. This will be 0. So the solution of this is not going to be very insightful, right? So there's this minimum regret approach, which is somehow a bit more robust to that problem. And so the idea here is that we're going to define this V start, which is somehow the maximum that you can do if you know the distribution, right? So it's like what we were doing here. We're going to call that function V star of Q. So if I knew what is the distribution of probabilities of valuations of customers, then I can pick the action that maximizes this. But I'm going to call this clairvoyant because in some sense, this clairvoyant knows what is Q, what knows how customer behaves. But in reality, I don't know. And then I'm going to look at this problem in which I'm going to look at what the clairvoyant can do in terms of value, minus what I will do, because this is my action. And so this is my regret. This is how much I regret what I did compared to someone who knows the distribution. And then I'm going to try the action that minimizes this regret. But then again, nature will pick a probability distribution that maximizes that regret, right? So again, I'm competing against nature, but now nature is trying to pick a probability distribution that maximizes the regret. And in this case, if you stop for a second and think about it, it's not obvious for nature that it wants to pick a distribution for which the valuation of consumers are always 0. Because in that case, there's nothing for me to do. The regret which actually will be 0, right? In that case, right? So this is more robust to those worst case situations. All right. So we're going to be using this way to think about the problem. And so what happens? Now take a customer. So what is a customer in this world? A customer is going to be someone who arrives at some moment in time and has a certain valuation for the product, right? So a customer is some sort of a dot in this space, right? So that's a customer. Arrive at time tau with a valuation fee. All right. Now what the company wants to do is to put a price trajectory. So how the price should look over time, right? And so what's going to happen with this customer? Well, that customer will potentially buy, because the customer is strategic, at this time tau in the future, and will pay this price P of this tau D, right? Now, if this is what happened with this customer, then what's going to be my regret? So the regret is going to be V, which is how much I could have extract from that customer. And this paper, what we do, we put some sort of discounting factor. So we penalize for actually having customer delaying the transactions. So this customer is buying at time tau. So the discounted payoff that a clairvoyant could have made is exactly this. It's essentially charging that customer the valuation and extracting all the rents. But because this customer, according to this price trajectory, is buying at this green dot, what the seller is actually collecting is this, which is the discounted at this time tau D of the price that the consumer pays, right? So this will be my regret if I were to use this trajectory. Let's say in customer, this customer is buying at this time tau. Okay. All right. So what is happening then in this setting? So we have customers which are again these dots with valuations and arrival times tau, and we're going to assume that they belong to some compact set, and of course there's a finite selling season. The seller is trying to come up with a price trajectory. What's the price that I would like to set for my products? So that's what we're trying to optimize over. And then we need to figure out how a customer will make a transaction, right? And the previous, I show you the customer buys in this green dot. So in this paper, we look at two possibilities. One is that customers are myopic. So what does it mean to be myopic? The customer will arrive at this time tau, and then we'll look at the future prices, and then we'll buy at the first time that the price is lower than the valuation. So as soon as possible. So it's not necessarily accounting for the fact that maybe the price is going to go lower later. As soon as I see a price that is lower than my valuation, I'm going to buy. All right. So that's a myopic customer. And a strategic customer is a customer that actually is trying to optimize. The customer is saying, look, if I wait, I'm going to be able to get, that product at a price, say PT. This is how much I will get in terms of utility. I have to discount it because I need to wait maybe more. So the customers also penalize delays. So they want to do this product as early as possible. But the customer will look at all the future prices and then will pick the price that maximizes, or will pick the time, I should say, that maximizes their utility, discounted utility. So that's strategic customers, a customer that is able to wait until the best time to buy this. Okay. All right, so so this is the order of events. Then the seller sets a price trajectory. Nature responds with some customer type V tau, and then the customer buys whether using this rule if the customer is myopic, or using this strategic rule if the customer is strategic. All right. Okay. Now, what we want to do then is to kind of formulate this as a regret problem. So again, this would be the payoff that the company will make. And again, the payoff that company makes out of a customer that has type V tau, and when the company set the price trajectory P would be precisely the price at which the buyer buys at this time D, and discounted by the time at which the customer buys. Now, the full information, so the clairvoyant will be able to find a price trajectory that will maximizes this. And again, this will be precisely to charging a price of V at the time of arrival and having that price constant, in which case the customer buys at that precise time, independent of their type, whether strategic or myopic. And the difference between these two things, the regret, and then again, what we're looking is for a price trajectory that minimizes the regret, knowing that nature will pick the type that maximizes the regret. So this, and then you can play a little bit with this regret function here, and you can show that there's two types of regret. There's a valuation regret and there's a delay regret that shows up. But let me show you that in a picture. So suppose that you have a myopic customer, right? So this is my price trajectory. So if this myopic customer is this customer B here, right? So this customer arrived at this time tau B with this valuation. The price is too high for that customer. The customer doesn't buy, but wait until the first time when the valuation is greater or equal to the price, which is precisely at this time dB. All right, and so this is where the customer will buy. Okay, now let's take customer A here. So if a customer arrives at this time TA with valuation VA, well, this customer will buy immediately, the myopic customer will buy immediately because the valuation is greater than the price. All right, so this customer buys this time TA. Now, why I show you these two customers? Because if this customer gives you this purchasing behavior, a customer that arrives at this point, capital B, will buy essentially at the same time, but will generate more delay regret because it has to wait longer, right? So customer B is dominated from a point of view of maximizing regret by customer type capital B. And the same thing happened here. This customer, buys immediately, but the regret is the difference. But this customer A has the maximum valuation, will have a valuation regret that is even higher because the difference between the value of that customer and the price that pays is actually higher. So in some sense, we only need to worry about customers in this boundary and this boundary when we think about nature picking types that maximize the regret. All right, so that logic actually means that we can characterize two curves, a lower bound and an upper bound curves, with the following properties. So if you want to come up with a price trajectory that has a valuation regret that is always less than R, so your pricing has to be high enough, higher than this lower bound. Right? So if you charge your price too low, there's going to be a lot of valuation regret because nature can come up with a customer that is willing to pay a lot for that. On the flip side, if you want to make sure that the price trajectory has a delay regret that is not larger than R, then the price has to be bounded above by a certain quantity so that people buy sufficiently fast. So there's these two functions. And so I'm going to plot this in this graph. So this is the upper bound, P capital R. This is the lower bound when I set R equals to 0.3. So any price trajectory in this kind of region, we have a valuation regret and a delayed regret that is bounded above by 0.3. So they will have a regret which is bounded above by 0.3. Now, if you try to cut the regret and say 0.23, then you're going to reach into this region where you want a price trajectory that is below the green but above the blue that's invisible. And so when you look at the optimal regret, you want to really find those two curves so that they actually keep some feasible region, right? And which is precisely when these two intersect. And so that's how you characterize the optimal regret that you can have in this case. And so in the paper, you can show that you have an optimal price trajectory with myopic customers. Any price trajectory is in between these two curves, this blue one and the green one. Any price trajectory here, it has to go through that point, and here will be a trajectory that will give you minimum regret. And which is interesting is that, for instance, the blue has this pattern that I was describing before. There is an initial markup, right? And then it goes through a markdown and eventually reach this clearance where the price is low at the lower limits, right? So the blue kind of give you some sort of a typical trajectory that we see out there, but with the advantage now that this is a trajectory that's been generated in an environment where you have no knowledge basically of customers' demand information, and you are essentially coming up with some sort of robust pricing strategy that minimizes the regret that you incur when you do this. Now you can do some sensitivity analysis for this. So this is your regret under an optimum trajectory, and so it's monotonically decreasing both in this ratio of the utilities, upper and lower. So some sensitivity about the range of the valuation. But more interesting to me, at least, is the sensitivity with respect to time. So if the selling season is longer and longer and longer, right, the regret is going to go down. But eventually you hit a point here, which is this T star, where actually longer selling seasons are not going to give you better regret, right? So this somehow tells you that if you're a company where you're trying to figure out what's the length of the same season that you would like to operate, when you have relatively limited information about consumers' purchasing behavior, and you would like to think about pricing strategies that are robust, then it turns out that there's some sort of a maximum length. You don't want to go beyond that. There's no need to go beyond that in order to minimize your regret, right? You don't want to be too short, because too short can certainly have very high regret, but you don't want it to be unnecessarily long when it comes to this. All right, I don't have the time really, but I just want to mention that these two curves that I showed you before are for myopic customers. But of course, we discussed the case in which customers are strategic. And when you have strategic customers, for the same numeric example, this would be the optimal price trajectory. And as you can see, you need to be much more conservative, right? Your price trajectories have to be lower, but not always, right? So you can see that the price trajectory are only lower at the beginning, but towards the end, they can actually be higher than your myopic, because essentially, you are trying to avoid customers to wait, right, and buy as soon as possible, but eventually nobody wants to wait too much, because there's also a penalty for consumers. So it turns out that your strategic customer pricing are somehow has a lower initial markup, but they are more stable through time as you incorporate that feature. Okay. Again, I don't have the time to go through the details of that, but I'm happy to chat offline with people that want to know more about that part. Okay, so that's basically all what I have prepared for today. And essentially, to summarize, I tried to give you some sort of a panoramic, high-level view of dynamic pricing as a field of research and practice. So hopefully by now you can see, and understand how companies are out there thinking about some of these questions. We focus more on the analytic pricing, which is how to manage a finite amount of resources in stochastic, where you have an environment where you have stochastic demand patterns. The first paper is the classical paper on this area and has many follow-ups. So let's give you a sense of what's the basic framework. And this second paper that I show you is really to give you a little bit of a feeling for how people like me and others have been thinking about expanding some of these ideas, and in particular, in this particular case, how to think about relaxing some of the assumptions about, we know customers and they're not strategic, but rather we don't know much about the market, we don't know what's demand, what should we do, right? How we should try to think about, and then this kind of framework of robust optimization, distribution-free optimization, where you don't make any assumptions on the probability distribution that kind of rules the market. Seems to be some sort of a, give you a perspective. I'm not going to say that this is the best framework. I mean, there's a lot of debate about whether these frameworks are too conservative or not, but at the very least, hopefully give you some food for thoughts in terms of how one can potentially expand, the basic framework in some directions. All right. So, and with that, I'm gonna just stop here.
Any questions? I know it's already the time. I want to thank René a lot for these three exceptional sessions. Sorry. I thought it was a question from Zen. Thank you. Thanks a lot, René. Really much appreciated. We'll as well. I will send an email as well, reminding you that the slides and the recording will be on the website, and also of our next session, which is a seminar-like. Rather than a course given by Omar Besbes from Colombia. Thank you again, René. Thank you all for your attendance, and we'll see you on Friday. Have a great one.
Thank you, Victor. Thank you, everyone.
Thank you, René.
It's fun.
Thank you very much.